All right, so the first silver problem is called find and replace. So in this problem, we're given two strings, both of length n. In one operation, we can take all instances of a character and replace it with another character. And then we want to find the minimum number of operations to obtain a target string or report that it's impossible. So I guess I've chosen a couple of samples here just to illustrate what the problem statement means. So in this first sample, we have the first string as AABC and the second string as DDEC. So we can notice that in this case, we don't need to change the letter C. We can change all the letters A's into the letter D, and we change all the letter B's into the letter E for a total of 2 operations. For this second sample, the answer is -1 because it's not possible to do this operation any number of times to change AA to BC. And we'll get into that in just a second. And then in this third one, you notice that, again, the C stays the same, but now we have to get A to B and then B to A. So what we can do is we can change A to another letter, let's say C, and then or A to another letter, let's say D, and then we change the B's to the A's, and then we change the D's back to the B's. So that takes 3 operations instead of the 2 that you might expect. So when it comes to solving these types of problems, it often helps to make observations and to solve a similar subproblem. So in this case, a good place to start is just to determine the case where it's not possible to find the solution. So in this case, if there are 2 positions I and j such that Si equals Sj and Ti is not equal to Tj, then the answer is -1. And then if we go back to the sample side, we can see that this is exactly the case here. So since there's 2 positions where we have the same letter in S, so we have both A's in here, and we have different letters in T, so we have a B here and a C here, then it's not possible because these 2 letters are always going to remain the same, no matter how many operations you do. So that's one condition for impossibility. Another useful technique is transforming the problem or transforming it into known techniques. So I think this is where a lot of contestants got stuck, because even after we find the case where it's impossible, it's not obvious where we should go next. As with a lot of problems, it helps if we model it as a graph. So because we know that each letter corresponds to exactly 1 letter in T, then we can draw it as a graph with each node as a letter and each edge as a relation between letters. So in this case, we know that A has to go to B, so we can draw an edge from A to B. B has to go to A, so we draw an edge from B to A, and then C goes to itself, so we draw an edge from C to itself. This type of graph actually has a special name called a functional graph, because each edge has at most 1 outgoing edge. And as we'll see, functional graphs have special properties that make it easier to solve problems on. So what we can do now is that the functional graph is divided into several components. So what we can do is we can solve the problem for each component separately and then just sum over the answers of each component. And then here's the point where you sort of just have to get like pen and paper and then sort of brute force out all the cases. So the first case is if the component forms a tree. So in this case, we have some letter here that wants to go to some letter here, some letter here that wants to go to some letter here, and then this letter isn't present in T. So by forming this tree structure, we can observe that a parent must be operated on before any of its children, which means we need to convert this letter into this one before we can convert this letter into this one. And why this is because if we choose to do this one first, for example, then when we get here, then we have no way of separating out which ones belong here and which ones belong here. So what we can do is we can just, for this case, we can just go by depth. So we do this one, this one, this one, and then this one, and then this one, and then this one. So In total, this takes n minus 1 operations for a connected component of size n. Okay, so then we have the tree cycle case, which might be the most complicated case. So what we have here is we have a tree, but in the middle you can see that we have a cycle. So and then for each node in the cycle, it sort of has its own subtree. So it's not obvious at first, but we can also do this in n operations. So as before, we need to, before we process a child, we need to process its parent. But since we have a cycle, it's not obvious where we should start. But what we can do is we can first eliminate one of the nodes by just we can first eliminate one of the nodes and then have this one matched to this one. To have this one, because this node needs to go to this node in the future. So then what we can do is we can just merge this node with this node because they have the same target. And then we can just reduce the problem to a tree, which we've already talked about. So this also takes n operations. And then the last case is just a simple cycle. Because we no longer have the property of one of the nodes having a subtree connected to it, we can no longer do the technique we did in the last problem. So what we do is we have an imaginary temporary node that we break the cycle with, and then we can go on from there. So this takes n plus 1 operations if a temporary node exists. So with the cycle case, we have to notice one last thing, that if all the nodes are in cycles, that's all 52 nodes that are in cycles, then we can't have a temporary node to switch to. So then the answer is also impossible. You can also think of it as if all 52 letters in T are present and S is not equal to T, then any move in S will result in sort of duplicates forming. So that means any move in S will result in less than 52 letters, which shows that the answer is impossible. Otherwise, the answer is the number of edges in our graph plus the number of cycles in our graph. Or rather than the number of cycles, it should be the number of pure cycles. So cycles that look like this and not like this. One last thing. So in regards to problem solving strategy, sort of the thought process behind this is to solve a simpler subproblem. So that would be identifying when the problem is impossible, to make observations, and then we also want to reduce to known techniques, because USACO no longer gives very template problems like BFS or DFS or things like that. So what we want to do is we want to sort of get through all of the fluff and reduce the problem to something we know how to do. So that concludes the analysis of Silver Problem 1.
Okay, and if you have any questions, please make sure to put them in chat. We're going to start with Silver P2. So I saw a lot of people in chat mentioned, should I use brute force? Or they mentioned that they passed bronze, but they couldn't solve any of the silver questions. If you weren't able, or if you looked at the questions and you saw all of them were hard, I would say this is the one that you can most easily solve because the implementation is pretty much a brute force. So the general idea of this question is you're given a grid of arrows. Each one of these arrows is going to represent a cow, and each one of them is going to switch directions every day. So for each cow, they're going to follow the direction of their arrows and then reach one of these vats. These vats each have a cost. So we're going to find the cost of a total day by summing up the cost of all of the individual cows. And then after the one cow's arrow switches direction every day, we're going to find the new cost at the end of every day. So this question, in essence, is a brute force. And the general idea is we need some form of algorithm to first find the initial cost of like before we switch the arrows. And then we need some form of algorithm to simulate the updates. So every time we switch an arrow and then find the new costs. So let's start with the first part. How do we find the initial cost? The basic idea is just to simulate through it. There are, I think, a variety of different ways you could do it, but some things that I've seen are using like a prefix sum version or recursion. But the basic idea is to simulate through it. And then for my implementation, we want to keep a list of the number of cows that leads to each cow. So for this yellow cow here, we're going to note that these 3 blue cows are going to pass through this cow, getting to the vat. And you'll find out why this is important in the next slide. Let me turn on the laser pointer. Okay, so once we've done like a simulation, we found the number of or the cost at the end of the day, we want to actually make a change. So with the information earlier, we know how many cows are going to pass through a certain cow to reach a vat. So we want to ask ourselves the idea of, if I were to switch the direction of this arrow, how many cows will be affected and by how much? Well, our initial thought is, if this cow switches directions from A to B, then the difference of the day is going to be B minus A, since it's the total amount from yesterday, and then we add the B cost, since this cow is now pointing to B, and then we subtract its initial A cost. But we also have to note that's not the only cow affected, because all of the cows, these blue cows, that point to this yellow cow are also switching their values from pointing to vat A to vat B. So actually, the cost of changing this arrow is the number of cows affected, which is, from our previous slide, the number of cows that lead to this cow, or these blue ones, plus 1, because this cow itself is affected, and then times B minus A. So in this question, if we just assumed that we were to switch an arrow and then put it back at the end of every day, that would be it. That's the end of the question. Does that make sense so far? Could you guys give me a yes or no in chat or reaction? Okay. Feel free to put questions in the chat if it doesn't make sense. But the problem with this question is that the arrows actually stay flipped until the end, unless they're flipped back. So once I move this arrow, the yellow cow, to this, when we add another query, it's going to still be flipped. So the thing we saw earlier, the number of cows affected, that value is going to change day by day, because when we flip this cow from down to right, the number of cows pointing to this bottom red cow here is going to change. Since initially here, it had 1 cow here, plus these 4 cows pointing to it. Now, because the yellow cow has been flipped here, this red cow only has 1 cow pointing to it. So if we were to directly get the initial value of the number of cows affected, we would get the wrong answer, because the number of cows affected has been changed. It's wrong. So we actually need to update everything from this yellow cow, everything from its old path, and everything from its new path. Because whatever cow it was pointing to on its old path is going to need to be subtracted for the number of cows pointing to it. And then all of the cows on its new path are going to gain 4 cows from these cows here. So we're going to subtract this number of cows for all of the cows on its old path and add all the number of cows to all of the points on its new path. It's also really important to note that it's not just the cow it's immediately pointing to. So for example, it's not just this cow that's going to get 4, but also every cow until you reach the end. So this cow here is also going to gain 4. So we need to update all of the cows, not just the one it immediately points to. And then the implementation for this is pretty much just a recursion. You can keep looping through from here and then to its parent, add 4, continuing until you reach the end. Okay, let's look at the implementation. Okay, this is actually n squared, but the initial calculation is O(n) squared to find the different connected components and initial cost. This is actually the most expensive part, so O(n) squared. And then also O(n) times query, because for every query node we're going to need to update, we're going to need to find all of the ones pointing to it and it's pointing to. So again, earlier, in order to find the cost of the day, we're going to find the number of nodes that point to this node and update the total sum. And then that's why it's important earlier where the change is, or where we need to keep a list of the number of cows that lead to each cow, because that way we can compute this in just, I believe, like 0.1. But then when we actually update, like here, this is going to cost Qn or n, because it's going to need to loop through and then keep updating until we reach the end. So this is in general a simulation question. You recursively find the next cow that it points to and update. Again, I would say that this is the easiest question. One way you could find the solution is, even if you didn't think it was going to pass, you should definitely try and write the brute force for questions. For example, for this silver question, it did pass. Okay, if you have any questions, feel free to put them in chat, but I think we're going to go over the third question now.
Okay, hello, I'm Ryan. I'll be going over this third question. Okay, so essentially, we're given Bessie's stuck on like an infinite number line starting at 0.0, and then every second she's either gonna move left or she's gonna move right until some time t where she's gonna give up and return a 0.0. And this adventure can be represented as a string of like left and rights. So like at the if character in the string, it represents like which way she goes. And then getting on times that she passed through two numbers, we got to figure out a path which minimizes the number of turns that she makes. So for example, in the top right, this is like an example of a number line of length 3, and then we're given like the passing values between the two. So like pass here will represent the number of times she goes between the first number and the second number, and pass on will represent the number of times that she goes through the second number and the third number. And we're guaranteed that we can construct a path given this pass 0 and pass 1. And so example, if n equals 2 and pass equals 2, 4, then the best path would be right, left, left. And if you look at the animation, we're essentially just going to be going, we're going to be like decreasing these counts as we go. And so at the end, everything's going to be at 0, 0. And then earlier, by like a path which minimizes the number of turns that she makes, that's just like saying how many times is she going to go right, left, or left, right. So here it's going to be right, left, right, left. And so the cost for this is 3. And so the idea behind this is that if we don't want to turn, then we shouldn't, because like then we could just like decrease the value of more of the nodes in the future while like doing the same amount of turns. So we just have to figure out when we're forced to turn. And if we look at the nature of the numbers, since we start at 0 every time, we're going to notice that if like this going between the first and second one is odd, then at one point we're going to move it passing to the right, and then we're not going to go back to the left again. So essentially, what I'm saying is that like if we have like this thing here and we have 1, then at one point we're going to go past here, making this like 0, and then we're not going to go back to this side again. So basically, if we have an odd number over here, it's like 3, then it means that at one point we're going to push everything towards here, and Bessie's going to end on this side here. And similarly, for an even number, if we had like, for example, 2 here, then we go right, left, and we won't go right again, because then that'll be 0. Does that make sense? And then given this, another observation we can make is that our like the pass away that we're given, it's going to be either, is it impossible to have an odd number? No. If we have 1, 3, for example, we could go boom, boom, like that. and that would be way, left, way. So, you don't have to end at the start for this problem. You can just end at any point. So that wasn't clear. But like if we have, for example, like 1, 3, 2. She ends at x equals 0. Really? I might have overseen that. Okay, but like generally, if we, yeah, because then in that case, then we can't have an odd number because then we'd be forced past that side and we can't go back. But okay, so let's just disregard the odd numbers. Then for all the even numbers, we know that like if once we go past some point, we're gonna go back, and this is like for example 1, then everything on this side should be cleared. So if we have, for example, 2, 4, then we can just go right and then left again, because then this will be 0, and then this also, and this isn't 0 yet. So if we ever make I equals 1, then we have to clear everything out on the right side. And this is because if we pass through this one again without clearing everything on the right side, then that's never gonna be finished. Okay. Or then some of this is kind of irrelevant then. But yeah, so we just had to keep track of the numbers of ones in a way and the number of ones that we do make. And then if we decide to pass it, then we're not going to be able to go back. So if you think of it as like having a left and right bound on here, then if we make this a 1, then we're going to move our left bound in here, and then we're going to clear everything out here. And then at one point it's going to be 3, 2, 1. And so we're going to be at this point here. That's going to be 1. And now we can relax this left bound because we know everything on the right side is going to be finished. So we can just push the left bound here, and we can travel back here. 0, and then this is also 1, so we travel that, and then we have a finished solution. And yeah, in the problem statement, it also mentions that the sum of all values of past I are going to be less than or equal to 10 to the 6. So we can just use an O of an approach where we just simulate Bessie's movement across this number line. And then in terms of implementation, we can do something similar to this mentioned here. We're just going to store all the breakpoints for left and all the breakpoints for right. And then we're going to try to extend it as much as we can. And here is the code for it. I'll paste the link in chat. But okay, then if she has to end back at x equals 0, then some of this won't really, a lot of this can be reduced because I consider if she can also go like right and not return at 0. So some of this is not going to matter, but the idea still works. So we're gonna maintain a current. So all of this is just IO. Basically, instead of just like storing the values in an array, we're gonna visualize it as like the number line instead, and just have the values of the next and then the previous. And it's gonna be a left bounds, it's gonna be a right bounds. Let me zoom in a little bit. And then we're going to have a current position, and it's just going to store the position, and it's going to store our direction, because whenever we can, we want to make sure that we maintain this position, or it's going to have an answer away. So while true, or while we haven't made everything a 0 yet, so we're going to move forward, or like, yeah, if it's forward, then we're going to move forward. And then if we reached a right bound here, we're going to try to push it out further. So we're going to just check, oh, did we 0 everything out to the left already? And then if we have, then we're going to just relax this right bound and then go that way. And this is just us moving to the right. Otherwise, we have to turn around. So we're going to be updating our state and then going to the next iteration. The same thing if a wipe bound is already forced, meaning that this is the furthest right this wipe bound can go, then we're going to turn back. Otherwise, if we haven't reached our wipe bound, then we're just gonna move right. And we're just going to say, oh, we're going to decrease this edge value by 1, and then if it's less than or equal to 1, then we're going to add that to a left bound. Because we got to keep track. If we make this a 1, then we have to do an extra check before we go back that way. Otherwise, we're going to be going backwards. So basically, it's going to be the exact same thing over here, except we're going backwards. For these if statements at the beginning of this loop, we're just saying, if it's already a 1, then we should be already having that in a left array. So we're just going to push it here. Because we also have the case. Actually, if everything's even, then we never have this case. So you can just remove this. But yeah. Does that make sense? Okay. If that makes sense, then I'm just going to cover a couple points for like how to come up with the solution. So the main idea for this one is just do casework or like basically if we have to reach you have to reach some end state, then what's like the most optimal to do? And so our casework here is if pass I equals 1, and then if pass I is equal to 0, or pass I is neither. And then we can just basically just like go through all these cases, see the best move to make. And at the end, this is just going to be O of n with actually O of sum. And basically just also consider a greedy approach, since a lot of silver problems are going to have some level of more complex greedy problems than you see in bronze. So basically just see, oh, if we're trying to minimize or maximize something, just be like, oh, if I don't want to increase the cost, then what should I do? Or like if I want to keep the cost at the same point, then what should I do? So just keep that in mind whenever you're solving a silver problem, and hopefully you'll get some ideas. But yeah, that should be about it.